All right, subscribers, welcome back to another episode of Science with Surbeck. Today what we're going to be talking about is section 14.1, which deals with the gas laws. Now, before we get going into the details of these notes, here are a couple of objectives that you should be able to meet by the end of this video. Objective number 1, state Boyles Law, Charles Law, and Galass Law. And objective number 2, apply the three gas laws to problems involving the pressure, temperature, and volume of a gas. So before we get into talking about these specific gas laws, what we need to take a look back at is what we can assume from the kinetic molecular theory. So the kinetic molecular theory, or abbreviated KMT, is a model that is used to explain the properties of solids, liquids, and gases in terms of particles that are always in motion and the forces that exist between them. So remember in chapter 13, we discussed those intermolecular forces, which were those dispersion forces, the dipole-dipole forces, and the hydrogen bonding. Those forces are what interact one particle to another, and the kinetic molecular theory helps explain what those forces do in terms of our particles involved in a liquid, solid, or gas. Now, with the kinetic molecular theory, or again, the KMT, we make 5 assumptions. So I'm going to go over a couple on this page, and then we'll continue on the next page of notes. But the first assumption is that gas particles do not attract or repel each other. And so what that means is because they do not attract or repel each other, these gas particles are free to move throughout the container they are in. Now, our second assumption here with gases is that gas particles are much smaller than the distances between them. And so what this assumption does is that it assumes gases have virtually no volume, and it allows gases to be compressed or expanded. Okay, so these are 2 of our 5 assumptions about gases through the kinetic molecular theory. We'll turn the page here and we will go to continue writing these assumptions. So assumption number 3 is that gas particles are in constant random motion. And so something to go along with this constant random motion is that the gas particles themselves are going to move in a straight line until they collide with another particle or the container they are in. And this assumption also leads to gases mixing with each other because they have this motion. Now, our fourth assumption is that no kinetic energy is lost when gas particles collide with each other or with the walls of their container. And so because those collisions do not result in a loss of energy, we consider them to be elastic. And we can even go one step further here with our fourth assumption, and that is this: because we have elastic collisions, it means the total kinetic energy is going to remain constant in a collision between gases as long as the temperature of the gas stays the same. And then our fifth and final assumption here is that all gases have the same average kinetic energy at a given temperature. Now, if we increase the temperature of a gas, what is going to result in is an increase of the total energy of a gas system. And on the flip side here, if we decrease the temperature of a gas, we are going to decrease the total energy of a gas system. All right, so I know there was a lot of writing and a lot of things we did here, but it's really important here to correlate the kinetic molecular theory and these assumptions, because it plays a role into the mathematical concepts that we'll discuss here in a few moments. Now, with this in mind, we're going to move on to our nature of gases, or how gases actually behave. So we start out here with just this statement. Real gases do not obey all of the assumptions of the kinetic molecular theory. But what those assumptions that we've just got done talking about do is they help approximate how gases will behave in the real world. Now, as we talk about this here business of the nature of gases, we need to keep in mind the following. So the following is this. The assumptions that are made by the kinetic molecular theory to help explain how a gas behaves are based on the following 4 factors. The first factor is the number of gas particles present. The second is the temperature of the gas sample. The third is the pressure of the gas sample. And the fourth is the volume of the gas sample. Now, again, we are going to see in this section here temperature, pressure, and volume, and how if we change just one of those things, something else is going to alter with a sample gas. And that brings me to my next statement. If one of these 4 factors are changed, it's going to at least affect one other factor. So let's use this business that we've just talked about here, and let's apply it to an example. So our example here is going to be a balloon being squeezed. Now, the best way to see this is through an actual example. So what I have here is a balloon. I've blown it up, and I don't have any more air that I can add into it because I have it tied off. Now, as I squeeze this, you can see that the balloon gets a little bit tighter in one area, and that is because of these assumptions or the nature of how gas is acting. So again, I let it go and it expands and fills the rest of the balloon. I squeeze it, we get that tighter portion of the balloon. Again, let it go. It has a little bit more room, more volume to expand those gases. So let's take into consideration what we just saw here. Number 1, the amount of gas is constant because the balloon is closed or tied off. The other thing to consider here is that the temperature of the balloon is assumed to be held constant. As I take the balloon and I squeeze it and let it go back and forth, I'm in my classroom here, and my temperature here in my classroom is pretty constant. There is not much variation in the temperature of my classroom. Now, this is a really important explanation of why we see the balloon get tighter, or the surface of the balloon get tighter. So as the balloon is squeezed, it decreases the volume of the balloon and pushes the gas particles closer together. So again, one more time, I just squeeze, and we are pushing those gas particles closer together because the volume has decreased. Now, we're going to get a little technical here in our next explanation. So again, we are squeezing the balloon. The surface of the balloon gets tighter because there's less volume. But now let's think about the particles, the actual gas particles contained in this balloon. So as the gas particles are pushed closer together when we squeeze the balloon, the collisions, keyword here, the collisions between the gas particles and its container increase. Because of this increase, the pressure of the balloon also increases. So that's why when we squeeze that balloon, we feel that surface get tighter, and when I let it go, I can poke a little bit deeper into the balloon. So I squeeze it, I can't poke as deep, but if I let it go, I can poke deeper, and that's because the pressure of the balloon is also increasing. Now, again, if I bring that balloon back and I squeeze it one more time, what I'm doing as I squeeze it is I am decreasing the volume, which results in the pressure increasing. And so all of this kind of ties together with our last two statements. So again, volume of the gas decreases, the pressure is going to increase. Okay, this stuff is fine and dandy, and it talks a lot about the details of why a gas acts the way it does, but now we can tie exact laws or mathematical equations to each of these things or items with a gas. So we start out here with Boyles Law, and it states that the volume of a given amount of gas held at a constant temperature varies inversely with the pressure. Now, this law here was found by Robert Boyle when he took careful quantitative measurements that showed when the temperature is constant, meaning we keep the same temperature. What he found is that if he doubled the pressure of a fixed amount of gas, the volume decreased by 1/2. Now, what Mr. Boyle also found was that when he reduced the pressure by half, the volume doubled. Okay, so again, Robert Boyle, what he did is he held a gas, same amount of gas at the same temperature. He doubled the pressure, and it resulted in a decrease of volume by 1/2, and then he reduced the pressure by half, and it doubled the volume. What he was able to do with this inversely proportional relationship is he was able to develop a formula for this law. And that formula is P1 times V1 equals P2 times V2. Okay? Now, our P1 stands for the initial pressure, and our V1 is our initial volume. And then on the flip side here, our P2 is our final pressure, and our V2 is our final volume. Now, you can use any pressure unit you want. You just need to know that the pressure units need to be the same. And again, you can use any volume unit you want, but the volume units need to be the same. All right, so let's put Boyle's Law to the test in an example problem. All right, so here is our example problem. It says a sample of helium gas in a balloon is compressed from 4 liters to 2.5 liters at a constant temperature. If the pressure of the gas in the 4.0 liter volume is 210 kilopascals, what will the pressure be at 2.5 liters? So again, whenever we get to these problems, we need to identify what we have and what we have for our variables. So you can see we have a unit for volume and we have a unit for pressure. That means we're going to use Boyle's Law, and that formula again is P1 times V1 equals P2 times V2. So all I'm going to do now is list out what I know and don't know and solve for my unknown. So our pressure initially is listed at 210 kilopascals. 4 liters was initial volume, and 210 is our initial pressure. So we have 210 kilopascals, and our volume, initially that volume of that balloon is 4 liters. So V1 becomes 4.0 liters. Now we go to our second pressure. If we read this, and we can read it again, but you won't find a second pressure. And that's because the problem says, hey, what is the pressure at when we compress the volume? So our P2, or our final pressure, is going to be a question mark. Now our volume, our second volume, or our final volume, the balloon is compressed to 2.5 liters. Now, again, I said pressure units have to be the same and volume units have to be the same. You can use whatever unit you want, but they do need to be the same. So I'm not too worried about our pressure units because that's the variable that we're finding, but I need to check out my volume units. We have 4 liters and 2.5 liters. We ask ourselves, are those the same unit? Well, yes, they're the same unit. So we can go ahead and plug these values into our equation. So our P1, again, is 210 kilopascals times our initial volume, which is 4 liters, equals our second pressure, which we don't know, times our second volume, which is 2.5 liters. Okay, so we need to get P2 by itself. It's attached via multiplication to this 2.5 liters. So we divide each side by 2.5 liters. And now we turn to our calculators here to help us out with this math. So what I'm going to do, in parentheses, I'm going to take 210 times 4, close the parentheses, and divide it by 2.5. So to help remember that here, I'm going to put these in a set of parentheses. So again, I'm going to take 210 kilopascals times 4. I need to put it in parentheses, 210 times 4.0. Close the parentheses, that's what's on top, and then we divide it by 2.5. We press enter and we get a value of 336. Okay, so 336 would be what our answer is on the calculator. And we need to talk about units. So I'm going to just put down 336. And then notice here, if we do this correctly, our units of liters will cancel out, and we're just left with units of kPa, or kilopascals. So this is 336 kPa, and that is our second pressure. Now, oftentimes here, because we only had what we call 2 significant digits, this number right here would be rounded to 340 kilopascals. So I'm going to put that down here. When we round to 2 significant digits, or sig figs here, this becomes 340 kilopascals. Again, I'm focused on getting the correct answer in our calculator, and then we can work out those significant digits. Okay, the other thing that I want to point out is as we decrease the volume, our pressure increased from what we originally started. That's exactly what Boyle found, and that's exactly what his law states. So now we can move on to another scientist who developed another gas law. And this gas law is known as Charles' Law. Now, Charles' Law states that the volume of a given mass of a gas is directly proportional to its Kelvin temperature at constant pressure. Now, I'm going to underline one key thing here, and that's the Kelvin temperature. We're going to get to that here in a moment, but keep that in mind when we go to solve Charles' Law. And so the Charles' Law was developed by Jacques Charles, who performed an experiment on gases and observed that as the temperature increases, the volume of a gas sample also increases when the pressure is held constant. Okay, so what we can do here, just like we did with Boyle's Law, is we can have a formula for Charles' Law. And so what our formula is here is that our V1 over our T1 equals V2 over or divided by our T2. Okay, so again, our V1 is our initial volume. Our T1 is our initial temperature. The V2 is the final volume. And the T2 is the final temperature. Now, again, our temperatures must be in the Kelvin scale. And I want to go into a little bit more detail of why we must be in the Kelvin scale compared to our degrees Celsius. So that brings me to this concept here, still associated with Charles' Law and temperature, but talking about absolute zero. So absolute zero is the lowest possible theoretical temperature, and at that temperature the kinetic energy of particles is zero, and all motion of gas particles at that point ceases. Now absolute zero is 0 on the Kelvin temperature scale. And just as a reminder, 0 Kelvin is equivalent to negative 273.15 degrees Celsius. And so just as a reminder, if we need to convert between Kelvin and Celsius, we can use the following formulas. So to convert 2 Kelvin from degrees Celsius, you are going to add 273.15. And again, to get our Kelvin temperature, our K, we take our degrees Celsius temperature that's given and we add 273.15. Now, to convert from Kelvin to Celsius, we simply subtract 273.15. Okay, so again, when we use Charles' law, we need to factor in absolute zero, which means we need to be in the Kelvin scale. Now, as we're on this topic, I want to go over the kinetic molecular theory's explanation of Charles' law. And so we start out here talking about at higher temperatures, two things happen. One, gas particles move faster. And so if gas particle moves faster, they're going to strike each other and the walls of the container more frequently and with greater force. Now, the big takeaway from these 2 points is that for the pressure to stay constant, like it does in Charles' law, the volume must increase so the particles have further distance to travel before striking the walls of their container. So what happens is if the particles go further, it's going to slow them down and it's going to reduce that pressure. So we increase the volume, the particles slow down, so that way the pressure of that gas, or the pressure that gas exerting on the container, isn't as high. Now let's go ahead, let's tie everything here with Charles' law and complete an example. So we start out here with an example Charles' law problem. And it says a gas sample is at 40 degrees Celsius and it occupies a volume at 2.32 liters. We increase the temperature to 75.0 degrees Celsius and we want to know what the new volume will be. And we're going to assume that the pressure remains constant. So again, we start out by writing our formula for this particular law. And another thing I want to point out is identifying the formula to use. Notice here we are given temperature and we are also given volume. So that's the reason we would use Charles' law. And so Charles' law says P1 divided by, messed that up, V1, meant to put V1 divided by T1 equals V2 divided by T2. Again, volume up here on top. Now, the volume of this gas was initially at 2.32 liters. So this becomes our initial volume of 2.32 liters. And then we go to our first temperature. It said that gas at a volume of 2.32 liters was at 40 degrees Celsius. Now, I'm going to pause right here because we cannot have degrees Celsius. We have to use Kelvin scales, and the real reason for that is we can't have negative temperatures when we throw it into this formula. And so what we're going to do to go from degrees Celsius to Kelvin is we are going to add 273.15 and we'll get our first temperature. So again, we're going to take 40.0 plus 273.15 And when we do that, we press enter, we get a value of 313.15. And so 313.15 is our temperature in Kelvin. Again, has to be in Kelvin. We need to convert that. And so our volume is what we're trying to find here. And our V2 in this case is going to be our question mark. And then our temperature, our second temperature that we raised it to, is 75 degrees Celsius. Again, we run into this problem where we have degrees Celsius and we need to convert it to Kelvin. So what we simply do is we add 273.15. And so when we do this, when we plug this into our calculator, we get 75.0 plus 273.15. We get a value of 348.15. And now we have all our players of the game, and we can plug this back into our equation. So we plug in here 2.32 liters. We divide that by our first Kelvin temperature, which is 313.15. And again, that is K for Kelvin. And we set that equal to our second volume, which we don't know. So we're just going to label that as V2. And we divide this by our temperature, our second temperature in Kelvin. Okay, so now what we need to do is we need to cross multiply. Okay, so what we're going to do is this. I'm not going to do any calculations. I'm going to set it up first, and then we will go and we will calculate. So the first thing that we need to cross multiply is our 2.32 liters and our second temperature of 348.15 Kelvin. Now I'm going to write it up top here, so I'm going to have 2.32 liters times 348.15 Kelvin. Now I'm going to set that equal to the second thing that I'm going to cross multiply, and the second thing that I cross multiply here is V2 times 313.15 Kelvin. Okay, so what we have to do here is this. We got to get V2 by itself. It's attached to this 313.15 number via multiplication. And so we are going to divide each side by 313.15 Kelvin. And again, divide each side by 313.15 Kelvin. Okay, so now what I'm going to do is I'm going to put 2.32 times 348.15 in parentheses, and I'm going to divide it by 313.15. So again, 2.32 times 348.15, close the parentheses. We divide that number there by 313.15. And we get an answer of this. I'm going to round to 3 digits. And so when we round to 3 digits, we get a volume of 2.58. So our second volume, or our final volume, is a value of 2.58. And again, we turn to our canceling of units. So our units of temperature cancel, and we're left with our units of L for liters. Okay, so that is how we would solve a Charles Law problem. Notice here, we increase the temperature from 40 to 75 degrees Celsius, and our volume also increased. Okay, so that is something to keep in mind as we go through and we do some of these problems. All right, so our last gas law that we are going to go over is the gas law called the Gay-Lussac gas law. And so the Gay-Lussac gas law states that the pressure of a given mass varies directly with the Kelvin temperature when the volume remains constant. Now, again, to help us recognize what we have here with Gay-Lussac's law, we also have a formula with this gas law. And so that formula is our P1, or our initial pressure, divided by our T1, or our initial temperature, is equal to our P2, or final temperature, divided by our T2, or final temperature. Okay, so what we need to do here is this. We need to identify our P1 is our initial pressure, and our T1 is our initial temperature. Our P2 is our final pressure, and our T2 is our final temperature. Now, again, our temperature must be in the units of Kelvin. And so as we're talking about pressure and the way temperature affects this, we can say this. Pressure is a result of collisions between gas particles in the walls of their container. And so if we have an increase of temperature, the collision frequency and energy is also going to increase. And with that statement there, we can also say this. Raising the temperature will also raise the pressure if the volume is not changed. All right, so let's put the formula of Gay-Lussac's law to the test and do an example problem. Okay, so it says here the pressure of a gas tank is 3.20 atmospheres, ATMs, at 22 degrees Celsius. If the temperature inside the tank is raised to 60.0 degrees Celsius, what will the gas pressure be in the tank? So again, identifying what formula to use is very important. And so we need to recognize this. We have a unit for pressure of 3.20 atmospheres, and we also have temperature. So if I didn't tell you it was a Gay-Lussac's problem, you should recognize I have pressure and I have temperature. I need to use Gay-Lussac's law. So again, Gay-Lussac's law said our P1 divided by our T1 equals our P2 divided by our T2. Okay? And so our P1 is our initial pressure, and it's the only pressure listed here in the problem. So our P1 becomes 3.20 atm, or atmospheres. Now, our first temperature here, that pressure of that gas at 3.2 atmospheres, is 22.0 degrees Celsius. But once more, we cannot have a temperature. We cannot have a temperature in degrees Celsius. So what we must do is add 273.15. So we add that 273.15, and that's because we need it in units of Kelvin. And also we can't have a negative temperature here in this particular formula. So we add 22.0 plus 273.15, and we get a value of 295.15. And that is in the units of Kelvin. Now, our second pressure here is our unknown. We want to know what the gas pressure will be. Okay? And then our second temperature, this gas tank is raised to 60 degrees Celsius. However, we can't have degrees Celsius, so we need to add 273.15 to get that temperature into Kelvin. And so we plug that into our calculator with 60.0 plus 273.15. We press enter and we get a value of 333.15 0.15. Okay, now what we do here is we put all information, all our values back into our formula. And so we would get 3.20 ATM divided by our first temperature in Kelvin, which is 295.15. And this is equal to our second pressure, P2, we don't know it, divided by our second temperature, which is 333.15. Again, just like I saw in my Charles Law problem, I'm going to cross multiply and just write these values down. So I cross multiply my first values here of 3.20 atmospheres times 333.15 Kelvin. I set that equal to the second thing that I cross multiply, which is P2 times 295.15. And so then I ask myself, okay, we got to get P2 by ourselves. It's attached via multiplication with this 295.15. So we divide each of those sides by 295.15 K. And so what I'm going to do in my calculator is this. I'm going to put this in parentheses, 3.2 times 333.15, and I'm going to divide it by 295.15. So we put this in our parentheses, 3.20 times 333.15. I close my parenthesis, and I divide it by 295.15. And I get a value here of 3.61 when I round it to our three significant digits. So we get a value of 3.61. Again, we can talk about units here. Our units of temperature cancel out, and so for units, we're just left with ATM for atmospheres. So 3.61 atmospheres would be our final pressure, or our P2 value. All right, so we introduced a lot about gases. We kind of extended what we did in chapter 13, talking about the intermolecular forces and the concept of gases. And we also applied it to our three gas laws, our Boyles, Charles, and Gay-Lussac's gas law. And so we will be doing a lot of mathematical operations. And one thing I did not mention is I'm not concerned about you knowing the name, but I'm concerned about you applying the information, the formula, to solve these gas problems. All right, we've had a great episode here. Talking more and more about gases and our chemistry here. I hope you have enjoyed this episode. And as always, if you haven't done so already, make sure you subscribe.